prove a number theory homework problem from Charles Vanden Eynden's textbook. This is problem 37, I think, section 4.4. But it's a result that links together something called Euler's theorem with linear congruences. It's not much to it, really, but it's still kind of interesting to see how it works out. The proof isn't too difficult. But what we have to have going on here is that these two constants, A and B, have to be relatively prime. Now, that's the notation. A lot of you guys, I'm sure, have seen it. If you haven't, we use the ordered pair, and it's not, the order really doesn't matter. 5 and 12 don't have any common factors, so they're said to be relatively prime or co-prime. Okay, I've seen it with GCF in front, or some, greatest common factor, greatest common divisor, or the GCF greatest common factor. Now, there's a result here that's very useful. I guess it has a lot of value in terms of congruence reduction. It's this Euler phi function result. Now, let's just talk about what phi at 12 actually means. It's a counting function. It counts the number of integers less than 12 that are relatively prime to 12. So 1, of course, and then 5, 7, and 11 get the job done right here, right? There's actually these four numbers are relatively prime to 12. Notice that 2, 3, and 4 are not relatively prime to 12. 6, 8, 9, and 10 are not relatively prime to 12. Only the numbers 1, the integers 1, 5, 7, and 11. So that's where we get this 4 here, okay? So it comes in super handy. The proof, I've been through this proof before. I'll just state it as a fact right now. Now, since what we're trying to show is this, it follows that we should multiply through by a raised to the phi of b minus 1. So phi of b minus 1 is kind of a complicated looking exponent right here. All right, and so that's what we do in this very next step. We take the given congruence that we're trying to solve and multiply through by this. And that's exactly what you see right here. Now notice the only thing else that really is happening here of any note is that this is a raised to the first power right here, right? This is a raised to the first power. Okay, now notice you have the same base here, a and a raised to this and this. So you can see how the ones cancel. When you add the minus 1 to the 1, it goes away. And so you're just left with a at phi of b right down here. But remember, this result that I did not prove, we just stated as a fact, a at phi of b is congruent to 1. Okay, so we can literally replace, and I'll put it there just for the sake of documentation, if you will. It's superfluous, but I mean, still, I want you to know that something happened. A at phi of b is congruent to 1. Okay, the right-hand side will remain unaltered, and so we'll get congruent to c. Okay, c just tags along the whole way. And then we have a raised to this exponent phi of b, and I'm going to try to make a phi the best I can. Okay, that is my attempt at a phi right there, ladies and gentlemen. Sort of a queer looking Q. So that's phi at b. The b enveloped in parentheses because phi is a function. Like that. Okay, so we've proved what we set out to prove. We can put a box here if you want. It's a little melodramatic to call it a proof. But it really involved two facts, essentially. This Euler phi function, and also just laws of exponents. That's it, the two results. This powerful result, the proof's a little bit, it's non-trivial proof, so we're taking it to be true. And then this next step is just laws of exponents. And we do have a solution. X is congruent to c, a raised to the phi of b function minus 1. Now let's just go ahead and show a concrete example here. Notice right here, I've done exactly what this result says to do. I wrote down my x here. See how the 5 disappeared? Now notice I have a 3 here. Phi at 12, as we've seen earlier, is 4. So 4 minus 1 is the 3 that you see right here, right? So all we have to do is reduce this number. Now notice this would be 250, but we can take advantage of the useful observation that 5 squared is congruent to 1. Okay, mod 12. Now I won't write down the mod 12, but 5 squared is congruent to 1 mod 12. You can think of it more than one way. 5 squared minus 1 is equal to 24, which is equal to 2 times 12, or you can think of it as just 5 squared is equal to 1 plus 2 times 12, if you prefer to look at it that way. Now notice what happens here, and it's a nice thing that happens here. 5 squared, literally, you can think of congruence as being an equality at the modular level. You really can. There's some difficulties with that, but for the most part, it's a decent paradigm. But notice 5 cubed is 5 squared times 1, right? But 5 squared is 1, and so I didn't say that right. 5 cubed is equal to 5 squared times 5, all right? So 5 squared is 1, so we still have a 5 left, and this would be congruent to 10. Now, a lot of you probably laughing. You probably already guessed that 10 was the solution. You can do that just by running through 0, 1, 2, 3, all the way up to 11, okay? So, again, it's something you can calculate by hand by just going through all the values in the congruence class, I guess they call it. Okay, but so we get x is congruent to 10. And it's not hard to check right here. You would get 50. If you put 10 right here, you would get 50 is congruent to 2, which is certainly true. 50 is congruent to 2, since 50 minus 2 is 48, and 12 does divide 48. So anyway, this is what we're trying to prove. This is just an example that uses the result. Hope you enjoyed.